In this section, we'll look at the task of optimization, and since we are in the topic of quadratics, we'll look specifically at the task of quadratic optimization. The simplest way to understand what it is about is to look at an example. We have a brick wall here, and we want to enclose a rectangular garden plot next to it. And we have got 40 meters of fencing to enclose it. The goal will be to find the dimensions of this rectangle such that the area is maximum. We don't know yet how long these sides here will be, so let's just say they are x meters long. Let us name the remaining side of the fence z, and we see that the relation between z and x is 2x plus z are the 40 meters of the fencing that we have. So we find z is 40 minus 2x, and let's not use the meters here. Now we can express the area A as x times z, replacing z by this equation star up here. We get x times 40 minus 2x, which equals 40x minus 2x squared. So actually now the area A is a function of the width x. So A of x is 40x minus 2x squared. Well, A of x is obviously a quadratic function. So in order to sketch it, let's find the y-intercept, the zeros, and the vertex. For the y-intercept, we look at a of 0, which is 0, so the y-intercept is 0, 0. For the zeros, we set a of x equal to 0, so we get 40x minus 2x squared equals 0. We can factor out 2x. 2x times 20 minus x equals 0, and we find x1 is 0 and x2 is 20. So we have the zeros are 0, 0 and 20, 0. For the vertex, we know u is minus b divided by 2a, which means minus b being 40 divided by 2 times a being minus 2, and we get in the end 10. Inserting 10 into the function equation of a, so v equals a of 10, and we get 40 times 10, which is 400, minus 2 times 10 squared, which is 200, so we get 200. So the vertex that we find is 10, 200. And now we can sketch the graph. Well, here's the sketch, the y and the x-axis. We just say the top here is 200, and here on the x-axis, the right border here is 20, because that's the 0. And we get now up here at 1020 the vertex, and here we have the 2 zeros, and we can sketch now the graph, which looks like this, facing downwards because we have a negative a minus 2. What is the maximum value of a of x? For example, if x is 20, we see a of x is 0. If x is around 18, let's say, maybe if that was correct, we might be somewhere around 50 here. Well, when is it the maximum? Obviously, at the vertex, namely then the value is 200. So in C, the question is, what is the maximum area of this garden plot? And since our function a of x tells us the area of this garden plot depending on the choice of x, we know, oh, we have to choose now x such that we get the maximum for a of x, which we said is up here. So the maximum area is 200 square meters, and it is obtained for x being 10, so using the vertex. The length z is then 40 minus 2x, so we get for z 20 meters, and as we said, the maximum area is then 200 square meters. So we have finished this example. Let us now fill in some definitions. The process of finding the maximum or minimum of a function is called optimization. In the case of a quadratic function, the maximum minimum value occurs always at the vertex, as we have seen before. Hence, finding the maximum minimum of a quadratic function corresponds to finding its vertex. That's actually the whole theory, and so we can look at the next example. We have here a 400 meters racetrack, which is built around a rectangle where two semicircles are added to it. The goal now is to build such a racetrack such that the area of this rectangle here is maximum. Here it should say sides and area. The first step now is to decide what x is. Let us use as x the side of the rectangle on the racetrack. Let us call the other side z. In order to describe our total racetrack, we'll need additionally the radius of the semicircles, which is drawn here in red, and we actually see immediately it's half of the side z. The area of the rectangle is just x times z. We now have to reduce it to be just dependent on x, so we have to express z in terms of x. So what relation is there between x and z? Well, we have one information we haven't used yet, that's the length of the racetrack. The length of the racetrack is 400 meters, and it consists of 2 times the x here, plus 2 times the semicircles. Well, this makes just one circle with radius r, so the circumference of a circle with radius r is 2 pi r. Z is obviously 2r, so let's use that to rewrite that as 400 equals 2x plus pi times z. Let's put the x to the other side. We get 400 minus 2x equals pi times z. And in the last step, divide by pi, change the sides, and we get z is 400 minus 2x divided by pi. Let's mark this as our equation star. So we can now write our area as a function of x, so a of x equals, using the star equation, x times 400 minus 2x divided by pi, which is equal to x times 400 divided by pi minus x times 2x divided by pi, and we get in the end minus 2 divided by pi times x squared plus 400 divided by pi times x. As we have said before, the maximum value of this area a of x will be achieved for the vertex. So let's find the vertex. So u is minus b divided by 2a. So we get minus 400 divided by pi, and the whole thing divided by 2 times minus 2 divided by pi. Well, we can rewrite that just as minus 400 divided by pi times pi divided by minus 4. The pi cancels out, and the minus 4 cancels out against the minus 400, and we get in the end this equals 100. And so we have found out what was asked for. The length of the two parallel sides is 100 meters. And the area of the rectangle would be 6,366 meters squared approximately, but that was not really asked for.